And this is one carbohydrate. Carbohydrate. Observe this structure. In this, so many OH groups are there. OH group, OH group, OH group, OH group, OH group, OH group. Poly, many hydroxy groups. Polyhydroxy, aldehyde. And it is having chiral center also. Chiral center. So optically active, because chiral center is present. So optically active polyhydroxy aldehydes or ketones are called as carbohydrates. Optically active because chiral center is present. Polyhydroxy aldehyde or ketones are called as carbohydrates. Okay, right. Coming to the classification of carbohydrates. Classification based on products on hydrolysis products. See, some carbohydrates when dissolved in water, they give smaller carbohydrates, and some carbohydrates do not give any smaller carbohydrate. Based on the hydrolysis products, we can classify the carbohydrates into several types, right? For example, this is one carbohydrate. When it is dissolved in water, it gives two smaller carbohydrates. This is one carbohydrate and this is one carbohydrate. Okay, and this is one big carbohydrate. When it is dissolved in water, it will produce so many small carbohydrates. Dash. This is another carbohydrate. When dissolved in water, it do not give any smaller carbohydrates. But based on the hydrolysis products, we can classify the carbohydrates into C. This is a disaccharide because this is giving two smaller carbohydrates. When this carbohydrate is dissolved in water, it is giving two smaller carbohydrates. So this is called disaccharide. This carbohydrate when dissolved in water producing many small carbohydrates. This is called polysaccharide. Saccharide means sugar, sweet in taste. Some carbohydrates are sweet in taste, so based on that we can call all the carbohydrates as saccharides. Clear? Disaccharide, polysaccharide, monosaccharide. Monosaccharides do not give simple carbohydrates. Upon hydrolysis, they do not give any smaller carbohydrates when dissolved in water. Clear? Okay. Now, examples list. Examples list is important. Let us see. So, what is the first classification based on the hydrolysis? Carbohydrate based on hydrolysis classified into monosaccharide and disaccharide also called as oligo, and polysaccharide. Saccharum means sugar. We know monosaccharides. Monosaccharides do not give simple sugar. Do not give smaller carbohydrates, or do not give any monomers. Examples of monosaccharides: glucose, sucrose. Glucose, fructose, mannose, galactose, ribose, arabinose, so many. Others also there: xylose, lyxose, galactose already, and thallose. All examples are covered in the PDF. Okay. And disaccharides definition is okay. They give two smaller carbohydrates. What are sucrose, maltose and lactose. Sucrose, maltose, lactose. Remember this code, small. S stands for, L stands for lactose. SML. Sucrose, maltose, lactose. Small. SML. Okay, disaccharides. Polysaccharides. Polysaccharides give many smaller carbohydrates upon hydrolysis. Examples of polysaccharides: starch, cellulose. Starch, cellulose. Anybody? Biology students. Glycogen and dextrin. Starch, cellulose, glycogen and dextrin. These are polysaccharides, produce many smaller carbohydrates. Okay, you have to by heart the list. I already given in the PDF. Okay, right. Next, based on reducing property. You know, in the carbonyl compound structure, you read toluenes, phthalate, benedics, right? Aldehydes react with the toluenes, phthalate, benedics. What about ketones? Ketones do not react with the toluenes, phthalate, benedics. You know this. Once look at this reaction. I am taking aldehyde and the toluenes reagent, right? Toluenes. What is active species in the toluenes reagent? AgNH3. Positive means let us consider Ag plus. Let us take directly as Ag plus. Toluenes reagent active species is Ag plus. Once look at this, what is happening here? This is undergoing oxidation, correct or not? Oxidation. Ag plus is undergoing reduction. The one which undergoes oxidation is called as reducing agent. So aldehyde is a reducing agent. Why? Because it is reducing Ag plus. So in a compound, if aldehyde is present, we can call that compound as reducing agent. In any compound, if CHO is present, we can call that compound as a reducing agent. Clear? In glucose also, see the structure of glucose, CHO dash 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 dash, the remaining structure will be there. In glucose, CHO is present. So can we call glucose as a reducing agent? Reducing sugar. So based on the reducing property, glucose is a reducing agent. Example, I am taking glucose example. Glucose is a reducing agent because it contains aldehyde. It reduces, glucose reduces toluenes, glucose reduces phthalates, glucose reduces benedics. Okay, the carbohydrates or the saccharides which reduce toluenes, phthalates, benedics reagents are called as reducing sugars. Clear? Once again, in any compound, if CHO is present, you can consider that compound as a reducing agent. Okay, in carbohydrates like glucose, galactose, aldehyde groups are present, so we can consider that compounds as a reducing sugars or reducing agents. Clear? Right. So based on the reducing property, we can classify the carbohydrates into two categories: reducing sugars and non-reducing sugars. Okay. Right. Another classification based on the reducing property. Reducing sugars. This is memory based only, like your botany, zoology, by hearting only. That's why I'm explaining fast. Reducing and non-reducing. Definition is clear. What are reducing sugars? Which reduce? Toluenes, phthalates, benedics. Examples: glucose. In fructose, which functional group is present? I think you in your college already over. Tell me fructose. Can I write fructose under reducing category? This is fructose structure. See, all of you. Which functional group is present in fructose? In fructose, which functional group is present? This is keto functional group. Sujan? Non-reducing sugar, fructose. Fructose also. That is alcohol. Fructose also a reducing sugar, even though it contains ketone functional group. I'll tell the reason. Okay, right. Important question. Glucose, fructose, galactose, so many erythrose, threose, halose. Okay. Non-reducing sugars, non-reducing sugars. And one more important point, these are all monosaccharides. You can consider all monosaccharides. First you will learn one chart. Okay, I given first that classification only, examples. All monosaccharides are considered as a reducing sugars, all monosaccharides. And in disaccharides, what is the code for disaccharide? Small, SML small, except sucrose. The remaining two are reducing sugars in disaccharides. Other than sucrose, the remaining two are reducing sugars. We will see the reason. Okay. All monosaccharides are reducing sugars. In disaccharides, except sucrose, all are reducing sugars. Non-reducing sugars which do not reduce Tollens, Valens, Benedicts. Examples are polysaccharides and sucrose. Polysaccharides are non-reducing sugars. Okay, right. Clear? First we classified based on the hydrolysis: monosaccharides, disaccharides, polysaccharides. Second classification based on the reducing property. Carbohydrates which reduce Tollens, Valens, Benedicts are called reducing sugars. Which do not reduce Tollens, Valens, Benedicts are non-reducing sugars. Non-reducing examples are very easy: polysaccharides and sucrose. Clear? Right. Next classification: carbohydrates classified based on the functional group present in them. If aldehyde group is present, then they are called as aldoses. Carbohydrates with the aldehyde functional group are called as aldoses. Carbohydrates with the ketone functional group are called as ketoses. Aldoses and ketoses. Aldose means carbohydrate with the aldehyde functional group. Ketoses with the carbohydrate with the ketone functional group. Clear? Let us see aldoses. See, this classification is important. See the trick. First, let us start with the glyceraldehyde. A three-membered compound. Three carbons are present in that. If you know how to draw glyceraldehyde, then you can understand remaining structures. How to remember this structure? Glyceraldehyde. This is called D-glyceraldehyde. In first year, in isomerism, you learnt about D, capital D, capital L. Capital D, capital L. Configuration. DL. Give numbering from bottom to top. 1, 2. At second carbon, OH group is present on which side, right or left? Then the compound is called as D isomer. Bottom to top, actually numbering should be top to bottom because aldehyde is high priority, but during DL we go with, from bottom to top. Okay. At second carbon, OH is on the right side. So D-glyceraldehyde. Right. Based on D-glyceraldehyde, okay, all these monosaccharides are derived from the D-glyceraldehyde. With the help of D-glyceraldehyde, we can draw all. Right. See the trick. D-glyceraldehyde is the basic compound. What is D-glyceraldehyde? CHO, OH is on the right side, CH2OH. Go left. Write this structure as it easily. CHO and give one space for the one horizontal line and write the second line as it easily. This part, bottom part is as it is. This part is as it is. We went left or right? We went left. Keep OH on the right side. Keep OH on the right side. Okay. Next. Go right. Write this structure as it is. CHO and bottom part. Bottom part is common. We went right. So put OH on the left. These are 4-membered carbohydrates, monosaccharides, aldoses. Let us give the name for them. What is D-isomer? If you give numbering at second carbon, if OH is on the right side, that is called D-isomer. Here at second carbon, OH is on the right only, so this is D. D-erythrose. It is a aldotetrose. How many carbons are present? 1, 2, 3, 4. Aldotetrose. Erythrose. This is D-threose. This is also D only. Aldotetrose. Aldotetroses. Why this is called tetrose? How many carbons are present? 4 carbons are present. Which of the following is aldotetrose? Answer is erythrose-threose. How to draw erythrose structure? Take glyceraldehyde as the basic compound. Go left. Write OH on the right side. Go right. Write OH on the left side. Right? Now what is the difference between these 2 monosaccharides, these 2 aldoses? OH groups are present on the same side. In which of the following 2 OH groups are present on the same side? Answer is erythrose. Erythrose isomer or erythrose. Erythrose is a compound in which 2 OH groups are present on the same side. Threose is a compound in which 2 OH groups are present on the opposite side. Okay. Right. Another major difference is, let us give the numbering from the aldehyde. See, we use reverse numbering while dealing with capital D, capital L configurations. But according to IUPAC system, from which we start? From functional group. 1, 2, 3, 4. 1, 2, 3, 4. Now you tell me, these 2 differ at which carbon? Differ at which carbon? Online students. Second and the second. Other students, you are not getting. No one is answering. D-erythrose and D-threose differ at which carbon? Second carbon. Correct only, no? Others, online students. Second carbon. So these are called as C2 epimers. See the new term, epimers. The carbohydrates which differ at carbon other than first carbon, if they differ at any other carbon except first carbon, then they are called as epimers. What are epimers? The carbohydrates which differ at carbon other than first carbon. Don't consider difference at first carbon. See the differences second, third, like that. Okay? Epimers. These 2 are which epimers? These 2 differ at which carbon? So these are called C2 epimers. C2 epimers, very easy. Pair, you can remember the pair. Erythrose, triose, C2 epimers, one pair. Erythrose, triose, one pair. Clear? You see alphabet, capital E, capital E. How to write capital E? Horizontal lines are same side or opposite side? Is this correct for letter E? Horizontal lines are on the same side only, na? In erythrose, similar groups are on the same side. Correct? And how to write T? Alphabet T. Vertical line, one line that side, one line this side. One OH that side, one OH this side. So in triose, two OH groups are on the opposite side. In erythrose, letter E, all OH groups are on the same side. Which of the following is an erythrose isomer? In any compound, if all OH groups are on the same side, that is called as erythrose compound, erythroisomer. Okay, right. This is very important classification. What is the basis for this classification? D-glyceraldehyde. D-glyceraldehyde. Now tell me, erythrose and triose are which epimers? C2 epimers. C2 epimers. Because they differ at which carbon? Second carbon. C2. Right. Again, left you wanted to go. Any urgent work? Left and right. From D erythrose, move left. When we move left, what we have to do? Give one space for new horizontal line, and this part is same. This part is same. OH, OH, H, CH2, OH. We moved left. So this is D-ribose. 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 Next, guess here. We moved right. So D-arabinose. Arabinose. Very easy. You no need to learn all the things. Just remember the relation. Pairs. Erythrose, triose, one pair. C2 epimers. Ribose, arabinose, one pair. C2 epimers. So what you have to remember? Pair, combinations. Erythrose, triose, one combination. Ribose, arabinose, one combination. But this is aldo. Triose or octose? Triose or octose? Pentose. Pentose. How many carbons are present in this? So this is important. This point is important. Sorry, 1, 2, 3, 4, 5. Aldopentose. Which of the following is aldopentose? Ribose, arabinose. Ribose, arabinose. One important question is there. Number of optical isomers. Number of optical isomers. How many chiral centers are present in this? 1, 2, 3. 3 chiral centers are present. What is the formula for number of optical isomers? 2 to the power n, 2 to the power 3. So how many? 8 optical isomers are possible for ribose and arabinose. For this, for last one, here how many chiral centers are present? Online students. How many chiral centers are there here? 1, 2. 2 to the power 2. 4. 4. 4 optically active compounds. For this. 2 to the power n is the formula. Clear? Now tell me the pair. Erythrose, triose. Ribose, arabinose. Erythrose is which glucose? Aldo, tetrose. Ribose, arabinose are aldo, pentose. We derived ribose, arabinose from erythrose 3-ose only, na? So we increase one carbon, right? Okay. Online students, are you following, all of you? Hello. From D-ribose. I'm not giving from D-arabinose, sorry. Not from ribose, arabinose. Same story, left. So we have to keep CHO. Next. Right. So OH on the left. Another combination, very important combination. Yes, D-glucose, glucose, and these are aldoses only, not ketoses. D-glucose and D-mannose. D-glucose and D-mannose. What is the relationship between these two? Which isomers these two are? Which isomers these two are? At which carbon they are differ? Huh? First carbon. C2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. All are C2 epimers only. All are C2 epimers only. They differ at which carbon? See? They differ at second carbon or not? Here OH is on the right, here OH is on the left. And the remaining structure is same. H, H, OH, 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 OH. Everything is same. But what is the difference? Second carbon. Just pairs you have to remember. Actually, they won't teach all these things in the college, correct? Correct only, na? Because of this toughness. Students will feel first difficulty, but this is very, very important classification. Okay? Pairs. First, D-erythrose, triose. Ribose, arabinose. D-glucose, D-mannose. D-glucose and D-mannose. Minimum, these are very, very, very important combinations. Glucose and mannose are which epimers? C2 epimers. C2 epimers. Okay? Right. Once again, see this. D-glyceraldehyde. Based on the D-glyceraldehydes, we are classifying the aldoses. 4-membered aldo tetrose, erythrose, triose, C2 epimers, one pair. If you feel any difficulty, just remember the names only. Okay, just remove the structures, just write the names like this. Classify with names only, without structures, at least. Okay, right. Aldo tetrose. Next. D-erythrose from D-erythrose. D-ribose, D-arabinose. Ribose, arabinose are aldo pentoses. How many carbons are present? 5 carbons. D-glucose and D-mannose. Just. Ribose, arabinose, D-xylose, D-lysose. Combinations. In the same line means all these are aldo pentoses. The same line. Aldo pentoses. D-ribose, D-arabinose, C2 epimers. D-xylose, D-lysose, C2 epimers. But all are aldo pentoses only, right? Structures are not important for this. For these two also, but for glucose and mannose, structures are important. Right, I said another classification, D-lysose, D-lysose. Observe carefully. I'll ask you one question. Give the numbering for this 1, 2, 3, 4, 5, 6. Observe these two, and very important comparison. Can you able to say, online students? All of you. 1, 2, 3, 4, 5, 6. Look at this. Where it is? Look at this. At the fourth carbon in glucose, D-glucose, OH is on the right side. In this compound, OH is on the D-galactose, very important. Glucose and galactose. D-glucose, D-galactose. They differ at which carbon? Fourth carbon. Everything is same. Remaining configurations are same, but they differ at fourth carbon. So D-glucose and D-galactose are which epimers? C4 epimers. C4 epimers. Clear? And we have disaccharides, right? In disaccharides, lactose is made up of these two only. So you should know the structures. Disaccharides also there, no, for the syllabus. This is very important. D-galactose and here D-thallose. D-thallose or tallose. At second, these two are different second only actually. We write OH on the left side. These are C2 epimers only. These two are C2 epimers only. But particularly I am giving the relation between D-glucose and D-galactose. They are which epimers? C4 epimers. At fourth carbon, difference will be there. Clear? Right, combinations, erythrose, threose, D-arabinose, D-ribose, xylose, lysose, glucose, mannose, epimers, C2 epimers, galactose, thallose, all are C2 only, very easy combination. I'll give the chart, prepare them, okay? Right. Carbohydrates, number of chiral centers, number of optical isomers. Erythrose. No need to learn the structure, just remember that first we wrote erythrose only, na? So how many carbons are present in that? Total erythrose is tetrose, but two are optically active. 2 chiral centers, 2 to the power n, 2 to the power 2, that is equal to 4. Erythrose, threose, one combination. Erythrose, threose. Next, D-ribose, arabinose, another combination. Ribose and arabinose. Ribose and arabinose are pentose sugars. And you know in biogeology, pentose sugars means total 5, remove 2 to get chiral centers. 3 are chiral centers. If carbohydrate is having 6 carbons, 6 minus 2, that is number of chiral centers, 4. 6 minus 2, 4. Like that. 5 carbons are there. So 5 minus 2, 3 chiral centers. 2 to the power n. So 2 cube, that is equal to 8. Okay, I given this also just by heart. If you learn the chart, everything will be easy. You are just listening now only, so it will take some time. First read and write without seeing, then you will get. Okay. Yes. This is about the aldoses classification. Now coming to the first compound, glucose. Glucose structural analysis. Pakka 1 or 2 questions will come. One question is 100% on the glucose analysis. See, we will take one unknown compound in a test tube. We will take a compound directly, or we will dissolve the compound in water, and we will do some tests. So based on the results of the tests, we can predict, okay, CHO is present, or alcohol is present, or COOH is present. Clear? Okay, glucose is given to us. We don't know its name also. Just imagine we have given some unknown compound solution. Now we have to analyze which functional groups are present in that. That is called structural elucidation or analysis. Structural analysis. Right. You know carbonyl compounds very well. Aldehydes, ketones structure. If aldehyde is present, that will react with HCN or not? Hydrogen cyanide. Okay. If aldehyde is present, that will react with hydroxylamine. See this. I am giving one simple reaction, HCN. What is the product? Tell me. What is the product here? What is the name of the compound? What is the name of the compound? Cyanohydrin. Cyanohydrin. Correct or no? Cyanohydrin. RCHOHCN. Cyanohydrin. In any compound, if CHO is present, that will give cyanohydrin. Clear? If one unknown compound gives cyanohydrin, in that unknown compound, which functional group is present? Aldehyde. Or ketone also. Ketone also give, na? Ketone also will give same product. Means aldehyde is present or ketone is present. That is confirmation test for aldehyde or ketone. Here also oximes. Hydroxylamine will get oxime. RCH double bond NOH. In any compound, unknown compound, if aldehyde or ketone groups are present, that unknown compounds produce cyanohydrin and oximes. That is the key. Okay, key point for us. Glucose is given to us. Okay. We treated glucose with HCN, we treated glucose with hydroxylamine, then we got a cyanohydrin and we got a hydroxylamine. Means in glucose, which functional group is present? Either aldehyde or ketone. We don't know. Aldehyde will give cyanohydrin, ketone will give cyanohydrin. Clear? By getting hydroxylamine, aldehyde or ketone, anything may be present. Clear? But aldehyde is not confirmed yet. Just we are thinking, okay, aldehyde or ketone may be present. We have to confirm whether aldehyde or ketone. See, first step, how to detect carbonyl compound in the glucose. Step 1, detecting carbonyl compound, aldehyde or ketone. Take glucose solution, add HCN. If you get cyanohydrin, then aldehyde or ketone is present. Take glucose solution, add hydroxylamine. If you get oxime, then aldehyde or ketone is present. Clear? What is the confirmation test for aldehyde or ketone? Which reagents are used? Glucose, HCN or NH2OH. HCN or NH2OH. When glucose reacts with HCN, it produces cyanohydrin. Means in glucose, aldehyde group or keto group is present. Actually, I drawn the structure of glucose. Just imagine you don't know structure of glucose. Before that I kept CHO. Just forget that. Clear? When we add HCN, if we get a cyanohydrin, then aldehyde or keto group is present. When we add hydroxylamine to unknown solution, if you get oxime, then aldehyde or ketones are present. Clear? So what are the confirmation reagents to identify carbonyl group? HCl or hydroxylamine. HCl or hydroxylamine. Glucose when treated with HCl producing cyanohydrin. Glucose when treated with hydroxylamine producing oxime. The above two reactions confirms presence of aldehyde or ketone in the glucose. Clear? Now let us confirm which functional group, aldehyde or ketone. Next, second test. Glucose when treated with I am taking a shortcut structure for the glucose. Glucose when treated with bromine water. Glucose when treated with bromine water. Gluconic acid is produced. Gluconic acid. Did you learn all these things in your college? Learned? Later. Glucose when treated with bromine water, it produces gluconic acid, a monocarboxylic acid. Monocarboxylic acid. This reaction confirms presence of aldehyde. Because bromine water is a mild oxidizing agent. You know, mild oxidizing agent oxidize only aldehydes. Mild oxidizing agents oxidize only aldehydes. Because glucose is giving gluconic acid, means in glucose CHO is present. CHO is oxidized by mild oxidizing agent only. So how to confirm aldehyde group in the glucose? By adding bromine water. Which of the following reagent is used to identify aldehyde group in the glucose? Which reagent? Bromine water. Which reagent is used to identify aldehyde or ketone in the glucose? HCl or NH2. First reaction. Now it is clear. Gluconic acid means it is a monocarboxylic acid. Clear? Right. With bromine water, mild oxidizing agent. Online students, are you following, all of you? So, once see this, all of you. This is unknown solution. Or consider it as a glucose solution. Once again, I am explaining. See if you don't get unknown solution. If we add HCl or hydroxylamine, cyanohydrin formation and oxime formation confirms presence of aldehyde or ketone. It is clear now? This is one unknown compound or glucose solution. When it is treated with HCl, it forms cyanohydrin, confirms presence of aldehyde or ketone. When it is treated with NH2OH, it gives oxime, confirms presence of aldehyde or ketone. Anything may be present. But how to confirm whether it is aldehyde or ketone? By treating with a mild oxidizing agent like bromine water. Clear? Confirmation is over for aldehyde. Right. Actually, we should not take like this, but to understand the reactions, I am taking like this. Because this is unknown, but we are confirming. To understand the reactions, I am taking like this. First, HCl or NH2OH is over. To confirm carbonyl group, whether aldehyde or ketone. Second one is aldehyde, bromine water. Bromine water confirms CHO. CHO is present. Now you tell me, this is 3 degree or 2 degree, this part. 3 degree or 2 degree? Online students run away, I think, by seeing that big. Are you there, online students? Are you there or not? Are you there? Is it okay for everyone? Everybody. You are not responding. I am getting fear. Your silence is afraiding me. Respond. What happened to you? This is primary or secondary or tertiary? Primary alcohol. If I say tertiary or secondary, we are thinking. Say confidently. Primary alcohol. Primary alcohol. How to identify primary alcohol? By treating glucose with a concentrated HNO3. Treating glucose with a concentrated HNO3. You know, primary alcohol when treated with a strong oxidizing agent. What is the product? In alcohol chapter you learnt RCH2OH gives rise to COOH, acid is formed, and aldehyde is ready. It is ready to oxidize with any mild or strong. It is always ready to undergo oxidation. So this part will convert to COOH, and middle one is as it is. Here actually I should not do it. Okay, and this is COOH. Very important. What is the product when glucose treated with concentrated HNO3? A dicarboxylic acid called as saccharic acid. Saccharic acid is produced. When treated with bromine water? Yeah. Sorry. Saccharic acid. Before that also I wrote like that only, na? Yes. 4 only, na? Yes. Clear? Saccharic acid is a dicarboxylic acid. Gluconic acid is a monocarboxylic acid. Number of carboxylic acid groups when glucose treated with bromine water. How many? How many carboxylic acid groups? One only. One only. Number of carboxylic acids. 1. Here 2. With bromine water, gluconic acid. With HNO3, saccharic acid. Saccharic acid is a dicarboxylic acid. Okay, right? Any doubt, online students? Is it okay? Name I given na saccharic acid. Gluconic acid, that is our already. Gluconic acid, saccharic acid. Glucose. What is the formula of glucose? How do you know? Based on this stone. Glucose when treated with HI plus red phosphorus. HI red phosphorus. It produced N-hexene, a 6-membered alkane is produced. So glucose contains 6 carbons and straight chain. Later this was proved wrong, cyclic structure only correct. But remember the product name. What is the product when glucose treated with HI red phosphorus and hexane is formed? This produces presence of 6 carbons. Okay. What is the product when aldehyde is treated with H2 nickel or reducing agent lithium aluminum hydride? CHO is converted to CHO converted to correct. CHO converted to CH. What is its name? What is its name? Sorbitol. Sorbitol is formed. Sorbitol. With HI red phosphorus and hexane. With H2 nickel or lithium aluminum hydride, sorbitol is formed. Sorbitol. Okay. Glucose when treated with first of all see this general reaction. AC2O, acetic anhydride. This is used for the acetylation. Acetyl group is introduced. See this. ROCOCH3, acetyl group. Acetyl group. If one OH is present, one acetyl group is introduced. If if compound contains two OH groups, how many acetyl groups are introduced? How many? Tell me. How many acetyl groups are introduced? Two acetyl groups are introduced. H will be removed and acetyl group. I explained about acetyl group clearly in the last classes. Acetylation, under acetylation concept. Monoacetyl derivative. This is diacetyl derivative. If we get a pentaacetyl derivative, means how many OH groups are present? 5. Glucose when treated with the acetic anhydride, it produced pentaacetyl derivative, means how many OH groups are present in the glucose? 5 OH groups are present. If 2 OH groups are present, diacetyl derivative. If 5 OH groups are present, pentaacetyl derivative. Pentaacetyl derivative. Okay. These are the tests. Clear? Next, another important. Are there online students? Hello? Hello? Glucose reacts with how many phenyl hydrogen molecules? Very, very important question. Phenyl hydrogen. What is hydrogen? NH2. NH2 is hydrogen. Phenyl hydrogen means phenyl hydrogen. Phenyl hydrogen. What is the reaction in carbonyl compounds? Elimination, addition reactions are there? No? Elimination, addition reactions. We did this in carbonyl compounds chapter. Minus H2. Can you tell me how many molecules will react with the glucose? How many moles? 1 molar, 2 molar, 3 mole? Most important in the properties of glucose. Any idea? 1, 2, 3, 3. How 3? There only one CHO is present. Okay. If one CHO is present, 1 mole will be consumed. If 2 CHO groups are present, 2 moles are consumed. But in this only one CHO is present. How it is possible? At second carbon, OH group is present or not? At second carbon. First mole, see, we use 3 moles. 3 moles of phenyl hydrogen. Remember, this question will come. Expected question. Glucose reacts with 3 moles of phenyl hydrogen. 1 mole will combine with aldehyde. Second mole is utilized to oxidize the OH group. Look at this. 1 mole is used to react with this aldehyde. Second mole is utilized to oxidize this. Second mole. 1 mole phenyl hydrogen over or not? See this. See this part. Second mole also utilized here. Second mole. Okay, after 1 mole consumption, second mole is used to oxidize this. 2 moles are over, and third mole is used to react with the C double bond. Oh, C double bond. Oh, look at this. First take aldehyde. This structure is common. Remaining structure I am not giving. Dash 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 dash. First mole NH2 NH PH. First mole reacts with the aldehyde. CH double bond N NH clear? Okay, dash dash dash. First mole is consumed to react with the CHO. Second mole NH2 NH Second mole is utilized to oxidize OH group. To do oxidation. Oxidation means removal of hydrogen. Two hydrogens will be removed here. This hydrogen, this hydrogen. So what you will get? What you will get? Ketone. This is common. C double bond. Sorry. Clear? Next, third mole will react with this ketone. So total how many moles? 3 moles. Very, very, very important. If you unable to understand all the things, just you remember how many moles are used. Okay, that is sufficient enough. Okay, 1 mole, second mole, third mole. If it's difficult to understand this concept, remember the answer. How many moles of phenyl hydrogen reacts with 1 mole of glucose? 3 moles. What is the use of first mole? First mole react with CHO. Second mole is used to oxidize OH group. Second place alcohol is there. No? Third mole is used to react with ketone. Okay, online students. Hello.